It's my honor and privilege to introduce to you our first presenter, Dr. Barak Dayan of the Department of Chemical Physics, a world leader in the field of quantum optics. Dr. Dayan came to the Weizmann Institute to do his PhD after 11 years of service in the Israeli Defense Force, in the IDF. He then went to Caltech for his postdoc and joined the Institute in 2008. He spends his time here working on the magic of photons, which have the miraculous ability to be in two places at the same time. When he's not in the lab, Barak tries to spend every minute having fun with his wife and kids. Unfortunately, for him, he hasn't yet perfected the ability to be both at home and in the lab at the same time. But who knows? He's very talented, he's very smart. Maybe he'll figure out a way. Ladies and gentlemen, Dr. Barak Dayan.
Thank you. I was 9 years old when I had my first quantum wow moment. I remember it very clearly. It was Friday, and my brother Jacob, who's 11 years older than me, just came back from the Technion where he had his quantum mechanics class, and he asked me, Baraki, come here. Listen, remember I told you about the atom? How the electrons orbit around the nucleus? Well, forget about it. That's not how it goes. Actually, there's this probability cloud, and the atom can sometimes be here and sometimes be there. And you know what's most amazing? What's most amazing is the fact that sometimes this cloud could look like that. Meaning that sometimes the electron can be here, sometimes here, but never in the middle. Wow. I remember being so puzzled by this. And it was only 10 years later, roughly, when I studied quantum physics myself, that I realized that the universe is even more amazing than that. Because things can actually be both here and there at the same time. Now, think about it. How is that even possible, right? So, how can you prove that something was both here and there? So, let me give you an example. When I drive back from Weizmann to Tel Aviv, I can take road number 4 or the Ayalon highway. Now, let's say I want to prove to my wife, when I get to Tel Aviv, that I traveled on both of them. So how can I do this? Here's the idea. I'll build something that sprays all the cars in the Ayalon highway with yellow paint, and all the cars in road number 4 with blue paint. And if indeed I can travel in both roads, then when I get home, I could call my wife and tell her, hey, honey, look at our car. It's green. So this is how you prove that something was at two places at the same time, right? You show that it was affected by things that happened here and things that happened here. Now, crazy as it sounds, nature allows this. This is real. And in fact, this is the basic idea behind quantum computers. So as you know, computers of today are composed of many transistors, with each transistor carrying a bit. And the bit can be either 0 or 1. Now just imagine how faster computers could be if we, instead of regular bits, we could use quantum bits, where quantum bits can be both 0 and 1 at the same time. So smarter people than me actually calculated this, and as it turns out, such computers could be thousands or even millions of times faster than today's computers. So this is a huge potential. So where's the catch? The catch is that these superposition states are really fragile. So nothing in the universe, nothing in the environment around them must know if it's 0 or 1, road number 4 or Ayalon. So if I really want my car to be green, then actually, by the time I get to Tel Aviv, nothing in the universe must know if I travel through here or there. Because if, let's say, if my car runs over one ant, or hits one molecule of air, then it's gone. Boom, it collapses, and my car is here or there, blue or yellow, not green. For this reason, physicists around the world in many labs have by now demonstrated this superposition state basically just with very tiny particles that you can control, such single atoms. And there are many challenges ahead still, but one of the major ones is communication between them. Because you see, if I want to communicate information from here to there, from one atom to the other, you can't use regular electrical currents like in regular computer. These interact with the environment and the superposition collapses. So, of course, there are many ways around it, but the most easy way to communicate a qubit is using light. In particular, single particles of light. Because actually, in the same way that electricity is composed of electrons, even light is composed of particles that are called photons. And to communicate one qubit from one atom to the other, we're allowed to use one photon, not more. Nature is not forgiving. You can't cheat. So one photon. As you imagine, this is not easy. Atoms are really, really small, you know. Photons are really weak, and it's a very demanding task. And this is what my lab focuses on. So in reality, it looks something like this. You see, it's a big room full of electro-optical equipment, many lasers. The heart of the setup are these structures, which are made of glass, silica, and they're really tiny, 20 microns, so you could fit 100 of them on the edge of a hair. And these structures focus and trap light. If we bring photons to them, couple photons to them, they travel around the circumference and stay in a very tight spot for a very long time, enough to make us do something with them. And these resonators are somewhere hidden in a vacuum chamber. And this is a picture from last month where we had to open it and close it again. And you see, it doesn't only look like open heart surgery, it feels like open heart surgery. And you must not allow even a single grain of dust to land on it. And you don't see the resonators, of course, because they're too small, but they're here on a chip that we fabricate here at Weizmann. And the experiment runs like that. We bring a very special fiber, which we fabricate ourselves as well, and we bring light into these crystal balls, and then we use lasers to trap atoms and bring one of them close to the vicinity of that resonator, so it interacts with the light inside. And these atoms can be made to represent two states. They can have different states, like 0 and 1, like a switch. What we managed to demonstrate last year was a scheme which allows to control that switch, to control that state with single photons. So, for example, if we send a photon from one direction, it clicks the atom to one state. We send a photon from the other direction, it clicks it to the other state. And how can we make a superposition state? Simple. We use well, not really simple, but of course. We use a beam splitter to separate the photon to two pathways. So it may arrive from the right and may arrive from the left, and that would project the atom to a qubit, to maybe 0, maybe 1, actually superposition of both. So in a sense, this is actually the quantum equivalent of a transistor. So a photon carries a qubit, and that qubit is mapped to the atom where it could be stored or processed, and the atom can send its own information out with the outgoing photon. Now, this is not only just an attempt to build a quantum computer. This is beyond that, because this is fundamental physics, and actually it's another small step in realizing the vision of this very, very wise person, Albert Einstein, who got the Nobel for, among many other things, for realizing that light is made of particles that are called photons. So using the technology in our lab that we have today, we could really start treating photons like real particles, do things with them. And for example, the last experiment we did half a year ago was we sent a pulse of light, and we grabbed just one particle, just one photon out of it, which is not as easy as it sounds. So, well, as you see, I find this very, very exciting, and I feel very fortunate to work on exploring such amazing and weird aspects of nature. Unfortunately, I have no way to solve that paradox of being in the lab and at home at the same time. I could use only the classical solution, which is to bring my kids to the lab. Now, for all those of you who are not experts, this is your chance. Listen. You see this cute little guy? His name is Oded. And as you see on his shirt, he's a quantum mechanic. This lovely lady is Tamar, and she's a quantum mechanic. And I'm a quantum mechanic as well. So next time that somebody on the street asks you, hey, do you know quantum mechanics? You can say, well, of course. I know 3 of them personally. Okay. Thank you. Have a very fruitful and enjoyable evening.